Okay, so hi everybody. Thanks for joining us. So today we're going to talk about conduit flow and conduit flow models, and we have a guest. Larry Martin is with us, and he's emeritus scientist. I think that's how you say it at
Yes.
USGS now. So
Yes.
recently retired, but Larry developed a lot of codes for the community, for the volcanology community in the last 30 years or so. So conduit flow models is one of them, but also ash fallout, tephra fallout, and then plume models as well. So today we're going to focus on the con flow model. So I'm going to let Larry introduce the model, and then we can all do an interactive session on Victor to use the Jupyter notebook that is related to that model, and then talk a little bit more about the model assumptions, and then what we can do or cannot do with the code. So yeah, Larry, it's up to you.
Okay. So I should say that I actually started working at the U.S. Geological Survey in 1990, and one of the one of the first things that I was tasked with was my specialty, or the thing that I was interested in most, was what happens to eruptions when you add water. And among U.S. volcanoes, there was a big question. At Kilauea volcano, we knew that although the historical eruptions there were mostly non-explosive, that the caldera itself was surrounded by tephras. For example, if you go to these areas around the west side of the caldera, um, there are meters of phreatomagmatic tephra deposits, and most of those tephra deposits were deposited in recent centuries, before about the early 1800s and after about the late 1400s. And so the question became, what under what circumstances do you actually get water mixing with magma at the summit of Kilauea, and what kinds of hazards do those pose? And so I I initially started looking at the deposit, but I have this tendency to model things. So I decided to start asking the physical question: if you have an eruptive conduit and a water table, under what circumstances can you drop the pressure in that conduit below hydrostatic and start getting water in during an ongoing eruption? And so you can draw a a plot showing the hydrostatic pressure in a groundwater system, and the groundwater system at Kilauea, the water table is nearly 500 meters below the surface at let's say, if we call the surface Uikahuna Bluff. So it's fairly deep. So you would have to drop the pressure in the conduit pretty low to actually get water in. And so if you imagine an eruption that is ongoing, so you're driving magma up the conduit, and you have this magma static pressure that is not simply static, it's dynamics. If you have actually flow through this conduit, and you have vesiculation, and it might even be pushing out an unvesiculated plug early in the eruption, what is the pressure profile going to look like, and how is it going to look compared to a magma static pressure profile, and how is that going to compare with say a hydrostatic profile from the groundwater system? And so you can basically write three equations for conservation for this system. If it's a steady state system, you can assume that the mass flux at any point in the conduit is the same. So the mass flux is simply the product of the density of the magma times its velocity times the cross-sectional area. And so that's what this equation up here says, that you have this product, which is the mass flux, and that doesn't change as you go up the conduit. And if you assume a straight pipe, then basically these two terms, the density and velocity, are constant. And if you were to assume, for example, there was no gas in the magma, that it had more or less a constant density going up, then you would simply be saying that the velocity is not changing as you're going up the conduit. So that's the mass conservation principle. The momentum is a bit more complicated, but it basically uses the states what terms are responsible for the pressure gradient in the conduit. The first is simply the magma static pressure. So the density of the magma is influencing the pressure, and that's why we have this variation in pressure with depth. But if the magma is actually flowing, then you have this term of rho u squared times some friction factor, and the friction factor depends on, in particular, on viscosity. I have a definition down here. So it's if we're assuming positive flow, which is basically laminar flow in the conduit, you have this viscosity term in the numerator, and then these terms like the conduit diameter and the velocity and density in the denominator, plus some constant term which becomes important when flow becomes turbulent. And then finally, if the cross-sectional area of the conduit is changing with depth, then you have a third term. And then finally, in conditions where you have, let's say you're above the fragmentation level of the conduit, and you have this mixture is coming up at many tens of meters per second, you can actually have the mixture velocity of approaching the sound speed. So this m is a Mach number, which is simply the mixture velocity divided by the sound speed, and this term says that you can't exceed the sound speed in the conduit except under certain circumstances. For example, if you look at the first two terms in here, these are always positive terms, and as the Mach number approaches 1, this term in the denominator goes to 0. So the only way you can have a finite solution to this is if the cross-sectional area of the conduit is changing. In other words, you have sort of a nozzle geometry where you're constricting flow at the outlet, and then you can have this whole term be finite. But in a case like that, we have what we call choked flow, where you have a sonic velocity going through a nozzle, and then accelerating as it comes out the top of the nozzle, and that's only happening at the very top of the conduit, and only when the cross-sectional area is allowed to change. If you have a straight pipe, basically you're limited to subsonic conditions all the way up to the top of the pipe. And then finally, the energy equation says that under steady state circumstances, the sum of the enthalpy plus the kinetic energy plus the elevation potential energy is constant. So, well, you can see that there's a lot of terms in here that have to be characterized. The density, in particular, and that varies with magma composition and gas content, and especially. So gas solubility becomes important, and a lot of researchers use this term below, where it says that the mass fraction of dissolved gas is basically it follows one of these curves that you see in the upper right, where sigma and beta are adjustable constants and in general, beta is 1/2. So typically the dissolved water content or the saturation of a magma increases with the square root of its pressure. But at the time that I had started working on this, Mark Iorso had recently published a paper where he was able to calculate the chemical potential of water in a melt of an arbitrary composition. And in order to do that, he would use some sort of reference chemical potential, and these interaction coefficients, W, which tell you how, say, the chemical potential of one constituent like water varies in the presence of other constituents like SiO2 and TiO2 and so on. And he, through a series of experiments in the lower right, you can see he actually worked out the values of all these interaction coefficients. So I contacted him shortly after I got involved in this, and he started working with me. And so we actually, before Conflow starts its simulation, it goes through the whole calculation, taking into account the composition of the magma to determine the chemical potential, and the chemical potential of water that's dissolved in the melt, when that is equal to the chemical potential of the gas phase itself, then you're at saturation. So it would go through this calculation at a series of pressures and come out with a best fit curve, like these curves in the upper right, that would match those calculations. It was actually a lot more complicated than it needed to be, but it gave me the opportunity to give a gas solubility that actually depended on composition as well as other factors. For the melt viscosity, there's also a very old paper by Herb Shaw from 1972, which I think has been superseded by several studies since then, that gave the log of viscosity as a function of two parameters, which both depend on composition. And those dependencies are too complicated to include in this slide, but it is, at the time that I was writing this, it was one of the few relationships available, probably the only relationship available that would allow you to calculate viscosity as a function of composition. But shortly after I started, Ka-Uwe Hess and Don Dingwell came out with another relationship which applied only to rhyolites, which was much more accurate in terms of how well it predicted experimental data. So for silicates, if you enter a composition in Conflow that has a silica value above 70%, we'll use this term, and you can see how these differ for a rhyolite melt at saturation. Another thing that has to be considered if you're calculating viscosity is the effect of crystals and bubbles. So Conflow uses this very simple relationship, which has been published ever since the 1940s, that gives if you have a melt viscosity, eta sub m, that the viscosity of the melt plus crystals is simply the melt viscosity times 1 minus this ratio of volume fraction of crystals to some theoretical maximum volume fraction, which is usually given as something like 0.6. And it shows that the viscosity increases and then asymptotically approaches infinity as you get to this maximum value. This matches experimental data only up to volume fractions that are about 35% crystals. So you get a warning in Conflow if you start to run something that has more than that, and you can still run it, but you have to agree to, you've basically been warned that it may not be accurate. And then the effect of bubbles can be either to increase the viscosity or to decrease it, depending on this capillary number. So if you imagine on the right-hand plot, a case where you have a capillary number that is low, and you can think of whipped cream as an example. When you start adding bubbles, the viscosity actually increases. Under cases where the capillary number is high, and you can sort of imagine something like cold tar with bubbles in it, the presence of the bubbles actually decreases its resistance to shear. So the capillary number is equal to this melt viscosity times the shear strain rate of the bubble times its radius divided by the surface tension that's acting to keep the bubble in a spherical form. So in the whipped cream case, the viscosity is very low and the surface tension is high, so you tend to have this increase in viscosity, whereas in the case of coal tar, the viscosity is very, very high. So you have a decrease in viscosity with increasing bubble content. Density. Okay, so I really went kind of overboard when I was calculating density. You probably could have assumed a constant density for the melt. But again, in the 90s, there was a series of papers published by Becky Lang and Ian Carmichael in particular that gave the molar volume of a melt as a function of its temperature, pressure, and composition, and the molar volume was calculated as a sum of the mole fractions of its individual components times the partial molar volume of that component, and that the partial molar volume was calculated as the molar volume at some reference temperature and pressure plus some correction for the current pressure of the melt system and another correction for the current pressure of the melt system. So this is the formula that's used. It's incorporated into Mark Ghiorso's melts model. But it allows you to calculate, for example, how the density of melts change as you add water. And there's a fairly dramatic decrease in the density of melts as you add water. I could probably give you a demonstration later using the Visual Basic version to show that. But it could be like 20% difference as you saturate a silicic melt with a few weight percent water. So for the gas, the ideal gas equation isn't really that appropriate for the high pressures that you see in subsurface systems. So I used the equations that are in the National Bureau of Standards steam tables. They were actually published as the Fortran source code in this 1984 publication, but Mark, he converted them into C, and then I converted his code into Fortran, and it gives much more accurate values for things like the density and other thermodynamic properties. For the crystals, you simply specify the density, and then for the whole mixture, the mixture is this weighted sum of the mass fractions of the three components divided by their respective densities, and then you take the reciprocal of that and you get the density of the whole mixture. So for the fragmentation, you can see in this upper right, this is a plot of the various profiles of some of the key components as they go up a conduit and how they change with depth. And you can see as you get to the fragmentation point, all these things change dramatically. The pressure gradient in the conduit drops dramatically because you're going from a bubbly liquid to a dusty gas. The volume fraction of gas in the conduit increases very rapidly as you're approaching saturation or as you're approaching the fragmentation point, because you have a very high pressure gradient and it's dropping pressure rapidly. But then the change in volume fraction gas is less rapid as you exceed it, and so on. So the question is, at what point does it fragment? And the traditional, say really published in the late 1970s by Steve Sparks, was to simply suggest that the magma fragments when you reach a gas volume fraction that's roughly the closest packing volume fraction of bubbles in the melt, which is something like 0.75. A more physics-based model was published by Don Dingwell and Webb in 1989, and that says that if you imagine magma coming up the conduit, and at any given depth, it's probably going faster than it was at an incremental depth slightly below that, because of rapid vesiculation. So you can imagine a sort of extensional strain in the conduit. So this epsilon dot is the extensional strain rate that the melt is undergoing as it's going up the conduit. And if that extensional strain rate exceeds some value that can be accommodated by viscous shear, and they formulated it as this ratio of an elastic modulus divided by the viscosity times an empirical constant, which they took to be about 0.01. If that extensional strain rate exceeds that value, then you have fragmentation. So I initially used this gas volume fraction of 0.75 as the criterion. Then I started playing around with this one, and it works similarly. There are some results that aren't exactly numerically stable under this situation, but I noticed when I ran the model yesterday that the version that I distributed was actually the one that uses this extensional strain rate criterion. And finally, I mentioned earlier that the sound speed becomes very important in these calculations, because as you're approaching the top of a straight conduit, the Mach number, which is simply the ascent velocity divided by the sound speed, approaches 1, and it can't exceed 1. So that's really it's basically a boundary condition at the top. So in order to calculate whether you're matching that boundary condition, you have to be able to calculate the sound speed. So the sound speed in any fluid is simply the square root of its bulk modulus divided by its density. And the bulk modulus for a gas, you have to specify there's two bulk moduli. One would be how much the volume changes with pressure at a constant temperature. Another would be a sort of adiabatic bulk modulus, where you're compressing the gas and it's heating up as you're compressing it because of adiabatic heating. And it is that second bulk modulus that we have to consider in this calculation. So the bulk modulus of the mixture of melt, gas, and crystals is simply the reciprocal of this weighted sum of the volume fractions of these components divided by their bulk moduli. And for the melt and for the crystals, I'm just considering the regular bulk modulus of those, whereas for the gas, I'm using the adiabatic bulk modulus. And so this is calculated from those thermodynamic relationships of Haradel that I mentioned earlier. So it's rather complicated. I realized after I had written all this to calculate conduit flow properties that you can calculate a lot of other melt properties from these relationships. And in the earlier version of ConFlow for Visual Basic, I actually had a visual interface that did those things. So if you want to actually solve these the way that it does it, it starts at the bottom of the conduit by assuming an initial velocity, and the initial velocity that it usually assumes is about 1 meter per second. And then it uses those equations and just does a straight ODE integration upwards using a fifth order Runge-Kutta method. And then once it gets to the top, it checks to see whether the top meets one of two boundary conditions. Either the pressure is at 1 atmosphere, which you only get in unusual conditions. For example, if you have essentially no gas in the magma, you can have almost no acceleration, and you can reach the top without approaching the sound speed. Or if you have a significant amount of gas, you're going to get fragmentation at some particular depth and rapid acceleration until it approaches the sound speed. And in that case, the upper boundary condition would be the Mach number equals 1. So what it does is, it's called the shooting method. You integrate upwards, check and see whether it meets one or of those boundary conditions. If it doesn't, then you adjust the velocity and try again. And so in the right-hand side, I show you the output from Conflow where I start. So it does a series of runs. You can see in this column, the third from the right, the initial velocity at the bottom of the conduit, this first row, is 1 meter per second. And then it gives you the final numbers once it's reached the top. And it shows that the pressure is well above atmospheric and the Mach number is well below 1. So it hasn't reached any of those two boundary conditions. So it goes back and tries 1.5 meters per second and finds that that doesn't do the job either. So after a series of iterations, it's up to 7.5, then 11. And then it finally, on this last run, using 11 meters a second, it gets to the top, and in the last point, it's only 1.5 meters below the surface, and you can see it's reached Mach 1 by that point. So it says, well, that's good enough, and then it writes out a series of other numbers that it's calculated what the final temperature is, the temperature change, the enthalpy change, the maximum theoretical velocity, which is the velocity that the mixture would achieve outside the conduit, assuming that the excess enthalpy is all converted to kinetic energy with no other frictional losses. And then things like the maximum water table depth that will allow groundwater influx, and so on. So anyway, that's a whirlwind explanation of how Conflow works. And that went on probably a bit longer than I was expecting, but hopefully it was useful.
Thanks, Larry. No, that was great. I don't know if there's any questions at that point for Larry. I've got one actually for you. So one of the boundary conditions is actually to say that when the mixture velocity reach Mach 1 or atmospheric pressure, then the calculation stops. So we assume that the mixture cannot go to the speed of sound. So is there any evidence that can actually happen, that we have some eruptions where actually, mixture velocity in the conduit were actually, approaching the speed of sound?
So it's hard to measure the sound speed in a real eruption, but I think that, well, Sue Kiefer wrote a paper a long time ago arguing that there are, what she calls geologic nozzles. So you can calculate the sound speed of mixtures, including, volcanic vents. I think geysers was another example that she gave, where you can show that these gas solid mixtures or gas liquid mixtures can have very low sound speeds if there's any significant amount of liquid or solid in them, like sound speeds around 100 meters per second or lower. And it's easy to get velocities that high in those circumstances. And so even if you look at a simple gas dynamics, like an ideal gas flowing out of a reservoir through, say, a constricting nozzle, you can do a calculation about what the upstream and downstream pressures are, what that ratio is that's required to get choked flow. And it's pretty low, like a ratio of 2 or more will give you choked flow, and we're starting with pressures well above that in an eruptive conduit. So I think for most explosive eruptions, based just on theoretical considerations, you almost certainly have choked flow in most cases. But then you probably also, we also know that conduits aren't straight pipes in reality. They, every crater that you've ever looked into, you can see that there's probably some constriction down there, and then it widens out. And it's at that point that it widens out that it can go supersonic and start mixing with air. So
yeah. So yeah, the assumption is particularly good if you have a cylindrical conduit that is like mostly constant, right, in shape. But if there is some kind of constriction and flaring up, then maybe the mixture can actually reach greater velocity than that.
Yes, it almost certainly does. Yeah. So what we're talking about is the point below whatever you can see at the bottom of a crater. That's the conduit that we're modeling.
Okay. Yeah, makes sense. So I'm going to share my screen, and I want to show you the Jupyter notebook that we actually built together with Sam, and we put on Victor. So like any other model, once you're on Victor on your hub, you can go to a terminal here, and then you can just type Victor setup, enter, and then you have a list of models that you can install on your home directory. So you can see Conflow is number 2. So all you have to do is like type number 2 and then enter. I'm not going to do it here because I already installed it, but that's going to install the Conflow model together with the Jupyter notebook on your home directory. So it's going to create a new folder called Conflow, where inside you're going to get the Conflow executable here, as well as the Jupyter notebook called Conflow here. So you can open the Jupyter notebook that is here. And again, like any other model on Victor, I strongly suggest you to first look at the documentation about the model before using it. So the plan is like for each of these Jupyter notebook, we will have a link to the documentation of the model. We have done this for a few models, not all of them. We have not done this for Conflow. So what I did is that I actually included the documentation of the model into the shared folder. So if you go in the shared, Victor courses, and then spring 2025, you will see a new folder called week 10. And in there, you will see 3 documents. They are PDFs. One is Larry's paper about the Conflow model, the 2002 paper for you. So I remember I already highlighted some of the most important information there. I'm using it for my volcanology class, so as well in the fall. So I strongly suggest you to have a read through that paper first. And then there's another paper that is actually talking about an upgraded version of Conflow that is called Comfort 15. That's the version that is actually installed on Victor that you can use. So I also strongly suggest you to read that paper, especially about the improvement that's been made to Conflow, from Conflow to Comfort, that you're going to see in the Jupyter notebooks with some new input parameters. And so it also goes through 2 examples using the model. One is Pantelleria green tuff, and the other one is the Etna 122 BC Plinian eruption. And it's also going through, a sensitivity of the input parameters to some output that the model is giving you. So it's pretty good paper to look at and to read. And then finally,
Sylvain,
yeah.
Sorry, just to make a clarification. So Confort is the Fortran version of Conflow. Confort 15 is Silvia Campagnola's version. There's the Confort. If it doesn't say 15, then it's sort of uses the traditional calculations of viscosity and solubility that I described in this, this morning. So the main difference is whether it says 15 or not, which determines whether it's Sylvia's relationships.
All right. Thanks. Yeah. So you can see, for example, in page 4 where they go through the model improvement in terms of the rheology, the decompression rates, and then the equilibrium bubble growth. And I can show you exactly what are the new input parameters associated with that. And then you got a manual here. So I wanted also to put that manual as a PDF from Sylvia that is also showing you a brief description of what are the new things that have been implemented in Comfort 15, and then in terms of crystals and also well as decompression rates, and then also there is a short manual explaining how to run the model. But now that we have the Jupyter Notebook, it's actually pretty easy to run. So, all right. So all you have to do is go through the different cells, right, and then click on the Run button here to run each of the cells. All the parameters are already entered for you. So first, what you want to do is to import all the libraries that I needed to run that Jupyter Notebook. And then we go through the input parameters here. So each of these input parameters are actually explained in the papers. So that's why we want to link the documentation to that. I believe these are the parameters for the Etna 122 eruption, but I actually found some differences with what was in the paper of Sylvia. So I actually have another one here, notebook that is called Conflow Etna, that is actually changing that some of these parameters. But you can go through these parameters. You can see that at the beginning, the first parameter is basically about how to run the model, whether you specify a conduit diameter or pressure gradient. Then you enter the initial and final pressure. And then you have these iteration parameters that is basically if you want the velocity to be adjusted automatically to reach sonic velocity at the exit, or if you don't want any adjustment, you put 1. And if you want the velocity to change, you put the number 2 here. The initial velocity that Larry was talking about at the base of the conduit, you specified it here, so 1 meter per second. And then you have the initial temperature and whether the temperature should be constant or variable. So the initial temperature here in degrees Celsius, and then you put a number 1 if you want a constant temperature, or 2 if you want the temperature to change as a function of depth in the conduit. And then some properties of the crystals and the gas. So the specific heat of crystals here, and then the percent of water in the mixture. Then this vesicularity parameter is basically whether you want gas exsolution to stop after fragmentation or not. So you put 1 if you don't want the vesiculation to continue after fragmentation, and 2 if you want it to continue. And then you got some conduit properties here. So the initial and final depths of your conduit, and then the diameter of the conduit at the bottom and at the top. Gravitational acceleration, the chemical composition of your magma here as oxides. And then here you have some inputs about crystals. So you can actually put the main crystal phases. So the first value is going to be I think it's the volume percent of your crystal phase, then the density, and then the aspect ratio. So in Comfort 15, you can actually look at the effect of the shape of the crystals on the viscosity of the magma. So you can specify that by this aspect ratio here. So I think the first phase here is plagioclase, so you can put an aspect ratio for the plagioclase, and then second one will be clinopyroxene, and then third one will be olivine, for example. So you can put an aspect ratio for each of these crystal phases here, together with their volume percent and density. Then you have a bubble number. So the bubble number is the BND, the bubble number density that you can estimate using petrographic analysis, using microscopy, and looking at the smallest size of vesicles in a thin section, for example. And you're going to calculate that as a volume in cubic centimeter. And you will put that number here, and that number is going to be used to calculate the decompression rates using the Tomaru equations. That's then going to be used to set up the initial mass flux in the conduit. And then you have the surface tension. Larry talked about that. That's going to be used mostly for the viscosity calculation and the strain rate fragmentation criteria. This parameter, I think, is the diffusivity of gas, if I'm getting it right. So diffusivity of volatiles, yeah, in square meter per second. And then finally, you got the fragmentation criteria here that Larry was talking about. So one is using the porosity, so this value of 0.75 for the fragmentation. And if you put a number 2, then it's using the strain rate criteria that Larry was mentioning earlier. So that's a lot of parameters, all right? But that's what you need to run the model. So make sure you go through these if you want to use your own values and your own Magma. Make sure that you look through each of these parameters, because each of them is gonna influence and control what you're gonna get in the end as a outputs. Right. So you can just run these cells. Then you can go to the next one that's going to create the Conflow input files, which is this one here, con.in.text. And then you can also select your output parameters. So you have a choice between 27 output parameters, and you can choose. So here we put 7 of them, but you can change that if you want to put more or less. So for example, here I choose number 6, 2, 3, 8, 5, 22, and 7, which correspond to this list here and these numbers. But you can choose whatever output parameter you want in order to actually get a value of for example, exit velocity. For example, if you want the exit velocity or the viscosity of the magma, etc. So you can choose that. And you just have to change the number in there, and it's gonna select a different output. Right, and then now we're gonna create all the files we need to run the model. So you can just go through cells 6 and 7 here, as well as 14, and we're gonna go directly to this one that's gonna create the input file, the in the text. You see it's just got updated here. So if I open it, now it's got a text. This is a text file with all my input parameters that are formatted for Conflow to run, as well as the output parameters that I selected with 7 output parameters. And then the next set is actually going to run the model. So if you click on run, you're going to see it's very fast. And what you get is actually very similar to what Larry was showing you with Visual Basic. It's actually giving you a summary of your input parameters. It's actually calculating first the decompression rates in megapascal per second using the Toramaru equation. It's giving you a summary of your input values, magma composition, and then all the input parameters that you chose. So automatic velocity adjustment. We're going to continue the exolution after the fragmentation. We use the porosity criteria here, and then how the liquid viscosity and the mixture viscosity is calculated, which equation is used. And then the code start to run using the velocity of 1 meter per second, and then calculating the mass flux, and then trying to reach one of the two boundary conditions, either the pressure is going to reach 1 atmosphere or the Mach number is going to reach 1. So as long as one of these two conditions is reached, the model is going to readjust the initial velocity by increasing it until we reach one of these conditions. So you can see we keep increasing it here, initial velocity. And then here we reach a point where by putting a velocity of 25 meter, initial velocity of 25 meter per second, the Mach number is actually greater than 1. So we're going to, decrease it slightly to actually reach a Mach number of 1, which is achieved here on that iteration number 12, where we can now have the mass flux in the conduit, and then we can also read the final exit velocity here, which is 116 meter per second, and that's basically the end of the code. So what you can do is use directly this table as an Excel spreadsheet. So if you run the next if you run the next cell, it's going to create an Excel spreadsheet that's going to actually have this output data in a table. Here we go. So we just created it here. It's called conflow.csv. So if you double click on it, you can see that you got your 7 output parameters that you selected, and then as a function of depth or pressure in the conduit, and you go from the base of the conduit to the top at the end, and you can read here the values, same values that you had in the notebook when the code was running. And then you can also plot your data. So if you just run that cell 18, it's going to actually plot the output data that you selected as a function of time. I think, yeah. And so you can actually have a look at this curve. These are not as nice as the Windows version, this plot, but we can improve them in the future. This is just a first version of this notebook, so we can actually make them a little bit nicer. For example, instead of having them as a function of time, I think it would be better to have them as a function of depth in the conduit or pressure, like it is in the Windows version. So something we can do quickly is just to change one parameter and see how that's going to affect, for example, the viscosity of the mixture or the exit velocity at the vent. So, for example, let's go all the way to the top here into the input parameter, and then, for example, what we can do is just change the temperature here. So we say, okay, we're gonna increase that temperature. Instead of 1100 degrees, we're gonna choose 1300. So you remember that temperature is actually decreasing the viscosity of the melt. So all things considered, we should actually reach higher velocity at the vent So we're gonna run all the cells again, and then we can quickly check how. So we had 116, and now we can see that we reach 238 meter per second. So it actually almost doubled the exit velocity by increasing the temperature of the magma. So that's one thing we can look up, and then now we can also try to change the water content here. So you can see the water content was 1.85. So what if I put 1.2, for example? So I'm going to decrease the water content of the mixture, which should increase the viscosity and the density of the magma. So I should actually get normally an exit velocity that is lower. So I'm rerunning everything, and then you can see that now I reach only 88 meters per second. And so that basically confirmed that relationship. So you can try other parameters like that. Some of them are actually affecting more the output than others. For example, the temperature and water are actually something that directly affect the viscosity of the magma. So actually, the code is highly sensitive to these parameters, and some other parameters are a little bit less sensitive. I was playing a little bit with the crystal content, but didn't get much changes in the output. One thing that I'm not really sure, and maybe Larry, you can confirm that, is I think the content should be the phenocryst and the microlights, but in the paper of Campagnolida, they actually have different values for the phenocryst and the microlight. And so I'm not sure how to change that here, or do we just do the sum of the two and then put them here as a sum?
Yeah, good question. I had forgotten that
Yeah,
Sylvia had added that. The original Conflow just assumed it ignored microlights.
yeah. So you see
Um,
here they got like phenocryst and microlights, and they say
yeah,
that in Conflow phenocryst and microlights are summed in a single phase and no aspect ratio is assigned. So I was not exactly sure here how we would exploit that. I think because the aspect ratio is still there, but
yeah,
I
yeah,
don't see
and
any option for like microlights versus phenocryst. So
right, right. I mean, if she, uh, yeah, she obviously used a slightly different formula than what I described earlier.
yeah,
Um, Given also she's considering aspect ratio, which the Roscoe-Einstein correction doesn't consider. Um, yeah, I'm going to have to read her paper again.
yeah. Well, I mean,
I'm
it's I think it gives you a good start to use the model, and this is an example, and of course, if you want to use your own values and your own magma and your own input parameters, you will probably have to look into the literature anyway to get some of these numbers here, especially the surface tension, the diffusivity or volatile and things like that. So, but basically, what the notebook is doing here is basically taking the model and then allow you to change quickly the input parameters and rerun the model and look at the changes in the output and plot these changes in the output pretty easily. So I really like that in that way that it offers you that modularity that we didn't really have before in the Windows version. And so yeah, feel free to play with the input parameters. Be careful when you change the input parameters. Make sure that they make sense, right? Don't put values that are not realistic, because of course you're gonna get some output that also doesn't make sense. So when you change the parameter, make sure you do it in a proper way. Um, and yeah, that's basically it. So I don't know if there was any questions about either the notebook or the code.
Yeah, I wanted just to make a comment that if somebody is interested in modifying the code itself, for example, adding different constitutive relationships for bubbles and crystals, the code is open source and it's in the shared folder. So you can copy it into your own folder, make this modification, compile it, and we can help with that. But I think the mod already consists of so many different features that it would be just kind of like special cases that want to do that.
I'd be happy to work with anybody who wants to do that.
Thanks, Larry.
Yeah, sure.